Okay, let's begin. Today's lecture, we're going to look at floating point numbers. We're going to actually spend 2 lectures on this topic. So we'll look at floating point numbers today, and then you'll take the midterm exam on Wednesday, and then we'll continue floating point lectures on Friday. Okay, this stuff is not going to be on the midterm exam. Probably will show up on the final, but yeah, not on the midterm. So don't worry about that. You know, the midterm. I'm still kind of refining some of the things, but you can expect all multiple choice, some conceptual questions, some interpret the code and figure out the output type of questions, and yeah, that's going to be on Wednesday. I'll send out a seating chart tomorrow, so be on the lookout for that. And then again, I'm going off of trust here, but if you're sick, don't come to the exam, okay? Nobody wants to take the exam sitting next to somebody who's like coughing and sniveling. That just nobody likes that, right? So if you're sick, stay home. And then just let me know, and I'll work with you to figure out a time for you to do a makeup, okay? Is that all I need to say? I think so. Oh, okay. All right, so this lecture is going to be like, we're going to start, the course kind of takes a shift from programming to computational statistics. And so computational statistics is really the idea that we use computing power to try to answer questions of probability and statistics that might be difficult to answer directly using kind of mathematical rules. And so your latest homework assignment, the one where you're simulating the Monopoly board, is an example of computational statistics, where trying to answer some of these probability questions about the Monopoly board would be challenging to do from a mathematical standpoint, because there's all of these like different rules and different this and this happens and that happens. And so again, not impossible, but it really requires a lot of kind of thinking in order to try to answer it mathematically. So we take the computational approach instead, and instead we kind of write up the code to put in all of the rules, and then we just let the simulation run, and that allows us to answer some of these questions. And so that's your current homework assignment, and then we'll take a look at some more kind of methods that apply and that we have to think about when it comes to computational statistics. But before we can really get into some of those methods, we have to talk about floating point numbers. We have to talk about how computers store numbers and represent numbers, because it's very, very different from real numbers. We often don't think about this. When you see a number represented on the computer, like our brain kind of treats it like a real number, but they're actually not real numbers, okay? So the big point of today's lecture is that computer numbers are not real numbers, okay? And so we'll dig into what I mean when I say that, and show you examples of where computer numbers behave very different from real numbers. Okay, so as far as real numbers go, there's lots of different ways you can define and construct the set of real numbers. Some of you will take Math 131A, real analysis, where you really get into a lot of the stuff about real numbers and do proofs and stuff. And then some of you will never take that class, and that's fine. But you can kind of just imagine the real number line, right? This infinitely long line that goes from negative infinity to positive infinity. How many numbers are represented on that number line? Infinitely many, okay? How many integers are there? There's infinitely many. you can pick two locations on that number line, and there's infinitely many values between any two locations. So there's infinitely many values between 0 and 1. And the weird part is that there's also infinitely many values between 0 and, say, 100 or 0 and 1,000, but there's the same infinity between 0 and 1 as there is 0 and 1,000. But it's like different infinities for like how many integers there are. There's infinitely many integers, but that's a different infinity from the number of from the value, continuous values between 0 and 1 and stuff. And so anyway, all to say, but those are the real number. Those are the real numbers, okay? And you learn certain properties in math. You probably learned these properties maybe like in 3rd grade. I think I have a daughter right now who's in 3rd grade, and like she had some math homework that dealt with some of these things. And then they come later up in algebra and things like that. But these are rules that you learn, and they're like embedded, and you kind of take them for granted. And it's absolutely true. These are true for real numbers, right? You have the associative property. You can do A times B first and then multiply that by C. Or you can do B times C first and then multiply that by A. You're going to get the exact same number, right? And then whether you put them, A times B or B times A or A plus B or B plus A, those are exactly the same. And A times B plus C is the same as, A times B plus A times C. You have this distributive property. And so these are all rules that apply to real numbers. Absolutely true, okay? But here's the challenge, and this is what I'm going to kind of point out later, is that these rules do not apply to computer numbers, okay? So the numbers that are on your computer, these rules don't work anymore, okay? And that can lead to a lot of kind of confusion and frustration if you're not aware of what's going on. And so I've got several examples of that, okay? There's a few other things. And we don't think about this in day to day, but if you think about it, it's like, oh yeah, that's actually true. Okay, so this number line, this real number line, this infinitely long number line, you can pick any location on it, and that location has a decimal representation. Okay, we can represent any location on that infinite number line using our decimal system. Some of them might require an infinite number of digits, but we have a way to represent it. So you think about like the number pi, and we cannot represent its full form, okay, because it requires an infinite number of digits, but there is, in our mind, there is a decimal representation, right? It starts 3.14159, something, something, something. And there's infinitely many decimal places, but there is a location, right? Square root of 2 has a representation. The number 1 has a representation. Even like the biggest number that we could possibly imagine has a decimal representation. And as far as decimal representations go, they are sums of powers of 10. And it feels so dumb to bring this up in a college class, but this was like a big deal, I don't know, probably in 2nd grade or something, where it's like, okay, this number 5,413.29, 5413.29, you would read it as 5,413 and 29 hundredths. This represents 5 1,000s because the 5 is over here, 4 100ths, 1 10, 3 ones, 2 tenths, and 9 100ths, and this represents the sum of all of these things. And that's what this thing is supposed to say. It's the sum of different powers of 10 multiplied by different digits, and then you have a sign to say either it's positive or negative. Okay, and then whatever number you have, you can also do scientific notation. Scientific notation is like a big deal in like chemistry class, and a lot of the sciences often deal with really big and really small numbers, And so we often turn to scientific notation to help us represent these really big and really small numbers rather than having to have a bunch of leading or trailing zeros, right? And so here we have an exponent, 10 to some exponent value or the order of magnitude. And then the part that's being multiplied by the exponent, we call that the significand or the mantissa, all right? And we still have a sign bit. And when you have normalized scientific notation, the rule for normalized is that you just have one digit in front of the decimal point. You have one digit in front of the decimal point, and that leading digit can't be a 0, okay? So that leading digit can't be a 0, and then you have a bunch of other things. So you can have that number 5,413.29. Technically, this is scientific notation. This is non-standard, non-normalized, but these numbers are exactly the same. You can represent it as 541329. Okay, 541,329 times 10 to the minus 2 1/100th, and that's their equivalent. Okay, the standardized scientific normalized scientific notation is 5.41329 times 10 to the third, right? So we would roll the decimal point 3 positions to the left, and when we do that, we say, okay, you've got to undo that by multiplying it by 10 to the third. And then, this allows us to represent really big numbers like, I think this is Avogadro's number, the size of a mole, I think. I don't remember. This is some other really small number. I think it's like Planck's I don't know, something. Okay. I don't know all of these things. All right. And okay, so anyway, it is true to say most of the values on the real number line have infinite decimal representations. Some of them have finite decimal representations, like the number 1/2 we can represent as 0.5, and that is an exact representation of the value 1/2. But any kind of irrational number that has an infinite decimal representation, even a lot of rational numbers like 1/3, if you wanted to represent in decimal, requires infinite values. 1/3 is 0.333333, and it goes on forever. Okay, and so if you wanted to represent 1/3 in decimal, you can't. you have to cut it out. You can do like a mathematical notation. You put a little bar over that 3 to say it keeps going on forever. But generally, like if you're going to type it into your computer or something, type it onto a screen or write it onto a piece of paper, it's always going to be an approximation. Okay, and then and approximations mean they're no longer real numbers. Okay, so most of the numbers on your computer are also going to be approximations. Sure, we can represent integers precisely. We can represent 1/2 precisely, okay? But other values, they are going to be approximations, okay? We cannot represent values with infinite decimal places. Like you could take all of the computer servers, all the data centers in the world, and you would not be able to represent the number pi exactly, okay? Because that requires infinitely many digits, and we don't have infinite storage, okay? When there's petabytes, and I don't know what's above a petabyte. There's lots and lots of storage, but that's not infinity, and then we would consider it a waste of all of the world's computing resources to try to represent one number, okay? But yeah, it cannot be done. It cannot be done. We just have an approximation, and we generally say, okay, 16 decimal places of precision. That's good enough, all right? And yeah, it's good enough. It's good enough to send rockets to Pluto, okay? And that's what we have. Okay, So let's see. Computers store number in binary representation, base 2 instead of base 10. Okay, but I'm going to show you a calculator that represents numbers kind of, internally it's actually binary as well, but on the screen it's a decimal approximation, and stuff happens, and so I don't know if you guys ever played around with an old calculator when you were young, and if you did something like 10 divided by 3 and you multiplied that by 3, what do you get, right? So with real numbers, 10 divided by 3 times 3, that's equal to 10, okay? Here I recorded a video of myself using a calculator, and and so I did 10, and I said 10 divided by 3, and what does the calculator represent? 3.333333. Okay, that is, that's not a surprise, right? So if you do 10 divided by 3, this is what the calculator says. And what else is it going to say? All right, of course, it's going to say 3.33333, right? This is the closest the calculator can represent for 10 divided by 3. Okay, but what happens if you take this number and you multiply it by 3? Okay, it's probably not a surprise, but if you do 3.33333 times 3, you're going to get 9.9999999, okay? And we're like, okay, that's fine. But if you think about that, there's something profound going on. We've broken one of the basic rules of math, right? Like if you wrote this answer down, like if you said, what's 10 divided by 3 times 3? This would have been like there's like certain tells, like if you use AI and you get and it says sure, I'll do that for you. And if you copy and paste that into your answer and you submit it, then it's oh, I knew you used AI, right? And I mean, this would have been stupid. But if you were in elementary school and they put this on the test and you wrote down this, the teacher would know you used a calculator to get the answer, right? Because this is a tell. This is a thing that this is not happening mathematically, but this is what the calculator tells you, okay? All right. However, this thing, all right, and it's stupid, but I also recorded a video of this. Okay, you do 10 times 3, you get 30. 30 divided by 3, that comes back 10. Okay, that's not a surprise. The computer is able to do that. Okay, all right, but the thing is, here's the thing. We've broken one of the basic rules of math. We said 10 divided by 3 times 3 is not the same thing as 10 times 3 divided by 3. Okay, when you use a calculator and you're using approximations of numbers, we break one of these fundamental rules of mathematics. Okay, and there's other things like if your calculator has a square root function, you could try this out. You could try doing, what's the square root of 2? It's going to be 1.41 something, and if you take that number and you square it, older calculators will give you something like 1.99998. Okay, not exactly 2, right? And obviously, if you do 2 squared, you get 4, and you say, what's the square root of that? The calculator will get it correct and say it's 2. Okay, but again, this thing, we've broken some rules of math. With real numbers, these should be exactly the same. But we're not working with real numbers is the issue. We're working with calculator numbers. All right, and so here are just some more examples. These are more examples, and I can do in R, you can try this out, okay? I can say, let's take the number 0.1 and store it as A. What is A? A is 0.1, okay? Let's take the number B, and B is going to be 0.3 divided by 3, okay? And what is B? And that says it's also 0.1, okay? But then if I ask, is A equal to B? That comes back as false, okay? And you're like, wait, what is A? A is 0.1. What is B? B is 0.1. Is A equal to 0.1? Wait, no, not A is equal to 0.8. Is A equal to 0.1? Yeah, that's true. What's B? B is 0.1. Is B equal to 0.1? It's not, okay? And that feels, that's like what? Okay? They should be equal. They should be equal. 0.3 divided by 3 with real numbers is 0.1, but for the computer, this 0.1 and this 0.1, they're not the same, okay? And again, it's kind of like 10 divided by 3 times 3. It's not exactly 10. Here's another example that could be frustrating. All right, so here I do a is 0.1 plus 0.2. All right, that's 0.3. I'm going to say b is 0.3. Okay, what's b? A is 0.3, b is 0.3. Is a equal to b? That comes back as false. Okay, and again, you're looking in the environment, and it says a is 0.3 and b is 0.3, but they're not equal to each other. All right, so what's going on there? Okay. Here's another example. All right, I've got a sequence, and I say, hey, let's go from 0 to 1 by 0.1. And I get 0, 0.1, 0.2, 0.3, 0.4, 0.5. And I say, okay, what's the fourth value there? That fourth value is 0.3. Okay? And I say, all right, let's store that as A. And I say, okay, B is 0.3. And there's 0.3 and 0.3, but these are not equal, okay? And this can be maddening, right? So here I'm going to make a sequence, again, from 0 to 1 by 0.1, and I have S, and I could say like, hey, which of S is equal to 0.3? And I'm expecting the fourth value to come back as equal to 0.3. But it says integer 0, okay? And here I have A, and here I have B. I could say which of S is equal to A, and it says, yeah, oh, the fourth value in S is equal to A, all right? But then I could say which S is equal to B, and it says none of the values are equal to B, right? And, you know, how did you end up with B over here? You got 0.3. How did you end up with A over here? You got 0.3. This is 0.3 up here. And you could imagine writing some kind of code where you have an if statement, or you have like, if this is equal to that, and you're expecting, right? If you're expecting if A is equal to B, you're expecting that to be true, and yet it never runs, and you're like, what's going on? And you're looking, A is 0.3 and B is 0.3, but then every time you do if A is equal to B, it keeps coming back false. It would be a frustrating experience to do something like that. Okay, these are just more another example. So here I have 4/5 times 3 times 5/4, and you're like, oh, finally I get like a whole number. Okay, I have an integer 3, and you're like, okay, so maybe when I'm working with decimal values, like weird things happen. Okay, fractional values, weird things happen. So okay, now I've got a whole number. A, and here I've got a whole number of 3 here, okay? And this is, I'm just messing around with, what is this, the associative property, 4/5 times 3 times 5/4, and 4/5 times 3 times 5/4, and yet this 3 and this 3, they're not equal to each other, okay? And here's a little bit of insight of what's going on. Oh, before I forget. First answer to your view quiz is D. D as in dog. D as in dog is your first view quiz answer. All right, so here's a tiny bit of insight as far as like why isn't this working? Okay, but then it just kind of perhaps raises more questions. All right, so you can say options, digits equals 20. And you can say, all right, what is, print a bunch of digits out so I can see what's actually going on. And so when you say 0.1, it's actually not 0.1. It's 0.1000000, something very close to 1, 0.1, 1/10, but it's got this extra junk here, 555 at the end. And I say, all right, well, what's 0.2? And 0.2 comes back point blah, 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 111. And you go, oh, okay, I guess that kind of makes sense, because if I multiply this by 2, I would probably get that. But then I say, all right, well, what's 0.1 plus 0.2? And I get this. I get 0.3000, and then I get 444 as the junk at the end. And it's like, how does that even happen? How does 111 and a 0555 add up to 4441? Like that feels weird, okay? Because these, like if I gave you these numbers on a piece of paper and I said add them up, you're not going to get this. You would get like 166 or something. And then if you ask what is 0.3 on the computer, it says it's 0.299999889. Okay, so yeah, something weird is going on. Okay, here's just like another example of some of the frustrations that you'd run into. Okay, so these should all be exactly the same. I have 0.3, I have 0.4 minus 0.1, I have 0.5 minus 0.2, 0.6 minus 0.3, 0.7 minus 0.4. These should all be 0.3. Okay, these are like with real numbers, these are all exactly the same. Okay, but on the computer, this results in 3 unique values. I have a 0.29999 ending with an 8890. I have a 0.300 ending with a 4441. And then I have a 0.2999 but ending with a 3339. Okay, so I have three unique values there, and it's like, yeah, that's weird. Okay, that's weird. And what's going on is that we are only able to represent approximations. Okay, and we're representing things in binary, and we're representing things in in binary scientific, and it's an approximation. And so that's what's going on, is that the computer approximation for 0.3 is different from the computer approximation from this point, 0.4 minus 0.1, and you're just getting different approximations that aren't exactly the same. Okay. All right. So yeah, this is what binary science, how we write things in binary. So in decimal, when you have the number 5,413, we said that's 5 1,000s, 4 100s, 1 10, and 3 1s. Okay. In binary, instead of adding powers of 10, you're adding powers of 2. So if you have the number 1101, okay, 1101, you have 1 in the 8's place, 1 in the 4's place, 0 in the 2's place, and 1 in the 1's place, or things like that. Okay, so you're going to be adding powers of 2 rather than powers of 10, and you have binary values. Okay, and so your binary digits can either be a 0 or a 1, and then they each represent a different power of 2. So here are just the first 16 numbers you can represent in binary with 4 bits. So with 4 bits, you can represent 0 through 15. And so 0 is 0, 0, 0, 0. Okay. 1 is 1, 1. 2 is, now I have a 1 in the 2's place and 0 in the 1's place. 3 is a 1 in the 2's place and a 1 in the 1's place. 2 and 1 make 3. Then, so again, the powers of 2 are the 1s, 2s, 4s, and 8s. So 4 is a 1 in the 4's place. 5 is a 4 plus a 1. 6 is a 4 plus a 2. And 7 is 4 plus 2 plus 1. Over here I have 8. 9 is 8 plus 1. 10 is 8 plus 2. 11 is 8 plus 2 plus 1. 12 is 8 plus 4. 13 is 8 plus 4 plus 1. 14 is 8 plus 4 plus 2. And 15 is 8 plus 4 plus 2 plus 1. And so this is how we represent everything in binary. And then this just keeps going, right? I would have a 1 in the 16's place. And then we would just kind of repeat this whole pattern, but now I have a 1 in the 16's place. And so the breakdown of the number 11, okay, in binary is we have 1 8, no 4s, 1 2, and 1 1. And so 8 plus 2 plus 1 make 11. Okay, I think most of you have been exposed to binary. If not, just take a moment to, go through this table and make sure you understand the pattern that we use to represent binary numbers, okay? We can also represent fractional values in binary, all right? So values to the right of the binary point, so because we're no longer in decimal system, we don't call it the decimal point, we call it the binary point. And so values to the right of that now represent negative powers of 2. So the first position to the right of the binary point is 2 to the negative 1, so it represents the halves. 2 positions to the right is 2 to the negative 2, or values representing 1/4. 3 positions to the right is values represent eighths. So if I want to represent the value 1/2 in decimal, it's 0.5, 5/10. The value 1/2 in binary is 0.1. Okay, one value to the right of the binary point is 1/2. Okay, 1/4 in decimal is 2/10 and 5/100, 0.25. That's equivalent to 1/4. In binary, it is 0.01. No halves and 1/4. Okay, 3 positions to the right of binary would be 1/8, 0.001. And then 0.011 would be 1/4 and 1/8, or 3/8. So 0.011 is equal to 3/8. In decimal, that would be 0.375 to represent 3/8. But basically, this is how we can represent fractional values in binary. Okay. A lot of our values, I would actually say most of the values, most of the real numbers have an infinite representation in binary. Okay, just like most of the values have an infinite representation in decimal, and things like 1/3 in decimal can't be have an infinite representation in decimal, 0.33333 going on forever. Similarly, in binary, most of the values have an infinite representation, and a lot of values, even values like 0.1, 1/10 has an infinite binary representation. It's 0.0001100110011 with 0011 repeating on forever. That's how you'd represent the value 1/10 in binary. And again, we cannot represent the entire number with infinite precision. We have to truncate it at some point, and we don't get the exact value. We just get an approximation. And so what's going on is when you try to represent the value 1/10 in binary, you have an approximation. When you try to represent the 0.2 in binary, 2/10 in binary, you get another approximation. And when you add those two together, you get another approximation. And that approximation is different from this approximation of 0.3. And that's why 0.1 plus 0.2 doesn't equal 0.3 in the computer, in R. And that's what's going on. So we're going to dive in a little bit deeper into how floating point numbers are stored on our computer. And so there is a computing standard, IEEE 754. This is the standard that of electrical engineers something of electrical engineers. They decided back in 1985 how computers are going to represent floating point numbers. All right, and this became standardized for the entire kind of computer industry. Prior to the standard, different computer manufacturers had different systems for storing decimal fractional values on the computer. And so software, when you wanted to write a computer program, you had different systems to represent it, and it was complex. Okay. Now this standard is used by all manufacturers, and so whether you buy a Apple computer with a Apple Silicon, or an PC with an Intel chip, or an iPhone, or an Android, or all of these different, NVIDIA produces chips, and Qualcomm produces chips, and AMD, all these different companies produce chips. They all adhere to this IEEE 754 standard. And so all of the weird things that happen with floating point numbers they happen at the hardware level, and it is not something unique to R. Okay, any computer program that you use that uses floating point numbers, whether it's in R, Python, C++, Java, they all have floating point numbers implemented in the standard. And whether you run it on a Windows machine or a Mac or an iPhone or some other thing, they all adhere to the standard. And so all of the weird things that happen with floating point numbers, it's universal across all computational devices. Okay, and I suppose somebody could, so like there's new technologies evolving, like quantum computers, and I don't know how they represent numbers, but it's different. And eventually there's probably going to have to be some kind of standard as far as like how numbers on quantum systems will be represented. But right now, as far as all the computers that we're using here, they all follow this thing, okay? And so this standard says, all right, the way we're going to represent numbers is we are going to represent numbers in binary, and we're going to use scientific notation, and it's going to be binary scientific, in a normalized binary scientific. So this is floating point. And so in normalized binary scientific, you have a leading digit and the binary point, and you have your trailing digits of zeros or one, and it's going to be multiplied by a power of 2, okay, because it's in binary, so powers of 2. One thing you'll notice is that the leading digit is always assumed to be a 1, okay, and that's because when you have normalized scientific notation, the leading digit can't be a 0, okay, and in binary, if it can't be a 0, it has to be a 1. Okay, so there's no point in storing a 1 because that's redundant. If it can't be 0, it has to be 1. Now, there is an exception where you can have a leading 0. That's called denormalized mode. I'll talk about that later, but for now, we're going to just always assume the leading digit's a 1. We have a bit for the sign, okay? So the sign is either going to be a 0 or 1, so either positive or negative values. We've got these bits for the significand, or we also call that the mantissa, and then we have bits to represent the exponent, which is going to tell us what power of 2 we are using. So in binary, like if we want to represent this number, 6.375, 6 3/8. In binary, okay, the way we would do this is we would take the number 6. In binary, 6 is 110, a 4 and a 2. Okay, no ones. And then 3/8, 0.375, 3/8 is no halves, 1/4, and 1/8. Okay, so this becomes, so 6.375 in binary is 110.011. Right? And then to make it in normalized scientific, I'm going to take the binary point and I'm going to roll it over to the left 2 places. And so when I do that, I'm going to get 1.10011. All right, so I have the same digits, but I've just rolled that binary point over, and because I've rolled it over 2 places to the left, I have to then multiply it by a power of, I have to multiply it by 2 to the power of 2. I have to multiply it by 4. So just to show that these are equivalent, this is a 1, this is a half, this is a 16th, this is a 32nd, and if you do 1 plus 1/2 plus 1/16 plus 1/32, you get 1.59375, and you multiply that by 4, and you get the same number, 6.375. 6 3/8. Okay. On the computer, we can say, well, how many bits do you want to use to store the number? Okay. And there's a few different ways we can do it. Single precision floating point uses 32 bits. Double precision uses 64 bits. And there's also a long double mode, which uses 80 bits. Most computers today default to using double precision floating point. But if you have like a limited, I don't know, if you have like a tiny little computer chip and you're trying to do something, you might use single precision floating point, which uses only 32 bits or something. R only supports double precision floating point, okay? But other languages, Python, C, and stuff, you can use single or long double or things like that. And again, this is implemented at the hardware level, so it's not specific to just computer language or system that you're using. This is all how it's going. Okay, so as far as double precision floating point, which is really the most common floating point system that is like the default for most things, we use 64 bits. Okay, and those 64 bits get allocated like this: 1 bit for the sine, 11 bits for the exponent, 52 bits for the mantissa. That adds up to 64. Okay, so as far as the sine bit, 0 for positive, 1 for negative. Okay, let's talk about the exponent. We have 11 bits for the exponent. Okay, 2 to the 11 is 2048. So that's how many unique values we can have in the exponent. Okay, the IEEE 754 standard says we are going to reserve all zeros and all ones for special cases. Okay, so that leaves us with 2046 values. And of those 2046 values need to be able to represent both positive exponents and negative exponents to get values, big values and small values. So we need both positive and negative exponents. And so they decided half of these values will be for positive. So that's going to be 1,023 values for positive. One of the values will be for 0. And then the remaining values will be for negative. Okay. And so that means I'm going to represent the values going from negative 1,022 up through 1,023. That is 2,046 unique values. And so negative 1,022 will get mapped to all zeros and a 1, basically 1. And 1,023 gets mapped to all ones and a 0, which is in binary 2,046. So this means we have a bias of 1,023. Basically, the actual value of negative 1,022, I add positive 1,023, and I get 1, and I store a 1. The actual value of 1,023, I add the bias of 1,023, and I get 2,046, and I store the value of 2,046 there. Okay, feels a little weird. All right, but this is kind of like, imagine I list off all 2,048 possible values in binary, starting from all zeros and ending in all ones. I've got 2,048 unique values. All zeros is a special case, all ones is a special case, and everything else gets mapped going from negative 1,022 to positive 1,023. So the actual exponent of negative 1,022, I add a bias of 1,023, and I get 1. 1 in binary is this. Negative 1,022, I add the bias of 1,023, I get 2, and 2 in binary is this. And, going to the end, 1,022 plus 1,023 is 2,045. In binary looks like this. 1,023 plus 1,023 is 2,046. In binary looks like that. Okay. When you have all ones, again, the special cases, when you have all ones, that's going to represent infinity, okay? Or nan, for not a number. So we have infinity and we have nan. Those can be represented, okay? And then if you have all zeros, exponent of all zeros, that puts you into subnormal or denormalized mode, which means you have a leading digit of 0 rather than 1. Okay, and we'll talk about those later. All right, so to kind of get into this, wait, how many answers have I given you? 1 so far? Okay, let me go ahead and give you your last 2. Second answer is A. Third answer is E, E as an elephant. So second is A as an apple, third is E as an elephant. So let's explore this using just kind of like a miniature version. All right, so here I'm going to say let's use only 8 bits, and we're going to just pretend like this is a miniature version of our thing. And so instead of 64 bits, we've got 8 bits. I'm still going to need 1 bit for the sine, and then the remaining bits, I'm going to have 3 bits for the exponent, 4 bits for the mantissa. Okay, and this will allow me to represent 256 unique values, or 200, not quite. Okay, but I've got 2 to the 8, so I can represent quite a few values. We're going to look at almost all of them. Okay, and we'll kind of count through a lot of them. Okay, all right. So first bit, that's the sine bit, 0 for positive, 1 for negative. Okay, simple enough. Okay, now you end up getting 2 zeros. You end up getting a positive 0 and a negative 0. Okay, the computer hardware knows that those are equivalent. Okay, positive 0 and negative 0. All right, 3 bits for the exponent. 2 to the 3 is 8, which means I have 8 unique values for the exponent. Again, we reserve all 1s for a special case and all 0s for a special case. That leaves me with 6 values. Half of those values will be positive, so I'm able to represent 1, 2, 3. One value is 0, and the remaining are negative. So I can really only represent going from -2 to +3. All right? This means I have a bias of 3 because -2 is going to get mapped to 1. -1 goes to 2, 0 goes to 3, 1 goes to 4, 2 goes to 5, and 3 goes to 6. So basically, I'm taking the actual exponent, I'm adding 3, and that's the number I store in binary. So if I want -2 as the exponent, I add 3, I get 1, and I store 1 in binary. Okay. If I want 3 in the exponent, I add 3, I get 6, and I store 6 in binary, which is 1, 1, 0, 4, 2, and 0. Okay. All 1s is special, all 0s is special. And then the remaining 4 bits go in as the mantissa, okay, which will be the digits that trail the binary point, assuming there is a leading 1. So it's going to be 1 point something 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 times 2 to the exponent. So if this is our 8-bit number in our mini floating point system, what does this represent? I've got 0 for the sign, 1, 0, 1 for the exponent, 0, 1, 1, 1 for the mantissa. Okay, so I sign, exponent, mantissa. All right, so if my exponent bits are 1, 0, 1, what is that? I can go back to my table and I can say, okay, 1, 0, 1 in the table, okay, is 5. 1, 0, 1 is 5, but I have an exponent bias of 3, so the true exponent is 2. Okay, so, or I can say, okay, well, that's 5, the exponent bias is 3, the true exponent is 2. The mantissa bits, so I got 0, 1, 0, 1, 0, 1, 1, 1. The mantissa bits are 0, 1, 1, 1, 1. Okay, so I put that in there. I get 1.0111. I forget what I was saying. All right, so I have a 1 plus no halves, a quarter, an eighth, and a 16th. Okay, 1 plus no halves, a quarter, plus an eighth, plus a 16th. I can multiply that by the exponent of 2 to the 2. Multiply that by 4. So I'm going to get 4 plus 1 plus 1/8 times 4 is 1/2. 1/16 times 4 is 1/4. So I get 5 3/4, 5.75. That's the decimal value that this represents. Okay, and then just going the opposite way, what if I want to represent 2.25, the decimal value of 2 1/4 in binary? Okay, so in binary, 2 becomes 1, 0, and then 1/4 becomes 0.01. Right? So to encode this, I have to go normalize binary scientific. I roll that binary point over 1. So I'm going to get 1.001. This is going to get multiplied by 2 to the 1 because I moved it over 1 spot. All right. So as far as the mantissa is going to be 001. Okay. And then I'm going to put in a trailing 0 because I have 4 spots for the mantissa. So the mantissa bits will be 0010. All right. 2 to the 1. If 1 is my exponent, I add my bias of 3, which takes me to 4, and I encode 4 in binary, which is going to be 100. So positive number, 0 for the sign bit, 100 for the exponent to represent 4 with a bias of 3, which becomes 1, and the mantissa bits are 0010. Okay. All right, we're going to continue this on Friday. And we'll look at some more examples and just some interesting things that happen. Good luck as you guys study for the midterm exam. Look for a seating chart, which I'll send out tomorrow. And we'll see you guys on Wednesday.